Okay, so today we're looking at 6.2. It's our last section period that I have to present as required, and some people are thinking, thank goodness. So keep in mind as we're going today, this is vectors, and we're going to see a lot of notation stuff that might, be familiar with some of our matrix stuff as we go through. At least with our multiplication and being able to combine things when we do scalars. But I will be, or I should say dot product, I will be able to today apply the dot product to vectors. Okay, and that's the scalar I was talking about. It's the result. Identify the angle between vectors, project one vector onto another, and find work, or no, not a job, but foot-pounds or Newton meters as used in science. I think we took that one out, to be honest. Unless I have a change. Let me see what we've got here. I don't think I have a changed packet. So, yeah, it's been pulled. Okay, so we got to make that adjustment. So as we're looking through today, vectors can be multiplied in two different ways, both of which are derived from their usefulness for solving problems in vector applications. The cross product, or vector product, or what they'll say is outer product, results in a vector perpendicular to the plane of two vectors being multiplied, which takes us into a third dimension and outside of the scope of this. So everybody go, yay! We're not doing that because it's curl, it's gradient, and other things. We're looking at dot product, or the scalar product, or inner product of a vector. This results in a scalar value. In other words, the dot product of two vectors is not a vector, but it's a real number. So we're going to learn the process for multiplying that. It is the important information conveyed by the number that makes the dot product so worthwhile. Okay, and we'll be able to use the dot product to help us find the angle between two vectors, or two segments even, as we're going through this as well. Let's see if we got this. Now, we may use the letters U and V, W, lowercase letters, to represent vectors. So I've got vector PQ as notation for U is the vector represented by vector PQ. And again, as a reminder, when you went through geometry, you went through vector notation with a half arrow going up top. Depending on the text, that's adjustable by the authors. So you, the user of the text, you, the reader, have to have used, hey, the situation and go, oh, okay, this is a vector versus array. Okay, so context is important as we're going through this. Other notations used include, we got vector component vector form AB, and then we have AI plus BJ because of the different components of the vectors, the way we can represent it. Now, the dot product in standard form, as we go through, get that up a little higher for folks. Whether I have it like this, okay, where I do this, or I have it like this, the answer is the same. I can do the dot product. It's just the U1, V1 plus U2, V2. So it's a little bit, I shouldn't put a parenthesis there, but it's a little bit like what we did with multiplication of our matrices. We had a certain order of it, and then we added them together, the result. Okay, we did row column for matrices, but we're just talking about it as the first term times the first term, the second term times the second term, and their sum. Okay, whether it's written out this way or if it's written out in vector component form. Okay, either way it's the same deal. Now, the definition of a dot product. I just take the A term times the A term, the B term times the B term, and I find their sum. Okay, the sum of the two terms product. And now we have properties of the dot product where we can talk about, let U, V, and W being vectors. I can talk about the vector dot product multiplication being commutative, and that's what this does. I have my order, doesn't matter when I do dot product, okay? But when we did multiplication of matrices, there was an issue with order, and the only time the order didn't matter is when we were working with the identity matrix. But so you keep these things separate and you kind of understand the situation as we're working with the context and what we're working with. If I have a vector U times U, I'm actually finding the magnitude of that vector. Okay, absolute value of U squared. Okay, if I'm looking at 3, I've got 0 times U, or U times 0, it's still the 0. And we go over a property called zero vector. Okay, because 0, if I have a vector 0, 0, it actually is a vector with no direction whatsoever. So it's not orthogonal to any, but or I shouldn't say it's not perpendicular to any, but it's orthogonal to all. I mean, we'll talk about that when we get there. And we also have grouping symbols with vectors. I have commutative property, no problem. Okay, and then we have associative property, no problem. It works as we go through. Whether I go u times v plus w, or u plus w times w, it'll work out that way. Looking at this, deciding which one's which with my distributive property, and then I've got associative there, whether I with a scalar multiple c as we step through. If I look at this first one, if we're just talking about property number 1, property number 2, we're not going to solve all the properties. I'm not going to show you how they're all defined. What we will do, though, is just hit on a couple. And property 1 is just talking about u times v is equal to v times u, so commutative property. And all I'm going to do is I'm going to just pop this in here and talk about, by definition of u times v, I know I can take u times v, and it'll be u1, v1, u2, v2. Remember, when I multiply them together, I can add them. But now what I'm going to do, I'm going to switch their order, okay? Because inside here, u and v can switch their order, so I can go v1, u1 plus v2, u2 because they're separate terms, my a and b being multiplied, so I can multiply it out of order. And what we're showing here is that we have a commutative property in multiplication, but our vectors have commutative property. So I can now bring this back to my v times u, and I have the definition of v times u. So it's a pretty simplistic way of looking at this proof, okay? But it's a proof on how the property 1 would be applied. Will I have you do it overall? No, but it's really talking about the idea of vector multiplication and how it's commutative. Now in property number 2, I'm looking at this idea of absolute value of u squared. Okay, u times u just gives me my u1 squared plus my u2 squared. But we're going to use it in the idea of working with magnitude, because that's that magnitude symbol squared. And when we work with magnitude, it's the square root of it, remember? So as I step through, I've got my u1, u2, and on my other u1, u2, it's the same vector. So according to my multiplication properties, I go u1 times u1, and plus u2 times u2. And now I've got u1 squared plus u2 squared as I step through this. But I can also represent this u2 squared plus u1 squared, u1 squared plus u2 squared as the absolute value of the square root of the 2 squared, because that's what I'm going to use. Because remember, this absolute value of u is the working with Pythagorean theorem. But if I square this, it's this here. So if I break it down this way, from here to this taking the, hey, well, if I take the square root of both but square it, I haven't done anything different, but I'm showing you that this multiplication can be the magnitude squared, and that's it, okay, as I do that dot product. Questions there? And that's kind of the mundane, but if I step through those properties, you'll be asked to do one of those 2 on your assignment. That's why I put them in. Okay. Finding each dot product. As simple and as straightforward as I can get it. I'm going to take 3 times 5 plus 4 times 2. That's all I'm doing. First term times first term plus second term times second term. I have 15 plus 8. I get myself a 23. Okay, so this equals a scalar. My dot product returns a scalar as predicted, as informed at the beginning. Now, in B, you're on. Go ahead. I know I left all the good sign stuff for you guys. You doing okay? Really high-tech stuff, right? Now, keep in mind the way we can house or make the vector look with their two different forms with the vertical and horizontal. It's still the same. So instead of the ij, I mean, you don't have to write it this way to do the dot product, but I'm just going to write it this way. As you can see, it's not a big deal. This is 2, -1. Okay, times 3, -5. It's the same idea. Okay, so you don't have to write it down to this form to do the multiplication. You can just say see your 2 and 3, and that's going to be 6. Maybe perhaps I'll step it down a little bit slower. So I got 2, 3, plus my -1 and my -5. Okay, so I've got 6 plus 5, and I'll have 11 to finish up my answer. Any questions about that?
So you just like completely dropped the variable?
I and J are there to let me know that's the first part of the component, and J is the second part. Okay, it's something that we worked with the previous day when we were doing this. If we had A, B, that's the same as AI plus BJ. Okay, and if I had 3 space, if I had A, B, C, it'd be AI plus BJ plus C, K as we step through it. Now, property 2 of the dot product gives us another way to find the length of a vector, as illustrated in example 2. But I mean, you know, I can go u times u in the square root, and we'll be fine. Example 2, using dot product to find length. Okay. Really, I'm finding the length of that, which is magnitude. Okay, remember, magnitude. What is that? I just take the first squared, the second squared, but I could go u times u, okay, and find that square root as I'm going. So go ahead, find the length of u, thinking dot product. And people are like, what, dot product? So I've got this going on, and that'll return 4 times 4. That's 4 squared, plus -3 times -3. Square root of. So I've got 16 and 9, should be 5. Now remember, they asked me to do it in terms of dot product. Okay, that's why I did what I did. We did it before, you know, prior to this. Every time I saw this, I was like, well, you know, I know that vector is 4 or -3. And so when I'm doing this, I'm going to do this, and that's the 4 squared plus -3 squared and their square root. So it's very similar to what's going on. It's just notation issues. You know, being able to recognize, hey, that's kind of the same thing as we step through. So you start learning about that vector dot product notation. And know that that dot product is going to return a scalar. Okay, now, let U and V be 2 non-zero vectors in standard position as shown. Do you recall something from chapter 5? Oh, I don't know. It looks like this. Law of cosines. Horrible thing, right? Well, if I look at this next problem, this being theta, this being that red, v minus u squared, okay, and b being, this being v, this being u, this is being v and u, so I got dot product going on there. If I consider that, because really I'm talking about the length of v minus u. The angle between u and v is the angle theta, and 0 is less than or equal to theta, and that's between that and pi, or less than 180. The angle between the two non-zero vectors is a corresponding angle, their respective standard position representatives. Okay, now here's the thing. If I wanted to find this without doing the law of cosines, I could do the law of cosines if I wanted to. There's a shortcut. It's derived from the law of cosines, and here's the formula that they give us. Okay, this is the formula we will be using, okay, in order to find the angle value between two vectors that they provide. Okay. So if theta is the angle between the non-zero vectors u and v, and notice they have to be non-zero because once it's 0 and I multiply the dot product, I don't care what it is, if I have a 0 vector and I have 0 times anything 0, that wouldn't show that the angles are 90 degrees between them because they'd be orthogonal at the time, and we'll get to that in a second. But where does it come from as I do the setup? This setup up here up top. I set this up here, so let's talk about that proof using law of cosines. Okay, so I've got this absolute value of v minus u, because that's squared, and it's absolute value as we go across. Okay, now if as I do that, notice that it's a dot product of v minus u times v minus u, and it's still here I'm doing the absolute value. So I'm just going to do binomial expansion. I had v times v minus v dot u minus u dot v and u dot u. And as you step through that, you're going to notice some stuff as we go. This is v squared. This is v squared. This is u squared. I'm going to make that a different color. And that's u squared. So I've got those together, and now if I start combining things across my equal sign, I start knocking things out. And this is just a proof of where this formula for theta comes from, to find theta between two vectors. Okay? So now, after I get to this point, I know that this and this will become 0 if I subtract it from both sides. I know that u squared will be 0 when I subtract it from both sides. And that makes sense, right? So it gets down to me saying that's negative 2 u dot v equal the negative 2 absolute value of u, absolute value of v, cosine of theta. Or I should say the magnitude of u, magnitude of v. Sorry for that faux pas. Now I'm just going to divide, okay? So I get to this point and I divide. Okay, and I put my cosine over here and I divided that by negative 2u minus v. Well, what happens is in part of my result, I got to take the inverse cosine and I'll have my angle. And my angle between 0 and 180 as I get it. So this is the formula we're going to use to find the angle between two vectors. Haas, you have a very inquisitive look in there. No, you're good? You happy? Okay, because all it is these things knock each other out, the blues and the greens, and we get down to this, and we find that inverse of cosine. So we're going to use it right now. So I actually got to find three things. Thing one, u dot v, which is 2 times negative 2 plus 3 times 5. Okay, that's thing one. I got negative 4 plus 15, it's positive 11. Thing two, and remember, I'm going to color code these things as I do them so you can see what I'm doing. Thing two, I need to find the magnitude of u, which is just taking, in this case, 2 squared plus 3 squared square root. So I got square root of 13. I got to find the magnitude of v, which is just negative 2 squared plus 5 squared square root. Okay, so that's the square root of 29. Are there questions on how I got the dot product of uv, or the magnitude of u, or the magnitude of v? Now, once I find those three things, I pop them in to my equation. Okay, and my last one was there. So now, theta is equal to inverse cosine. And remember, I have to have my calculator in mode. My mode's got to be degrees to make this work. uv is 11. Square root of 13. Square root times square root of 29. And I close it off. But making sure that your calculator is in the right mode is a big deal as we step through this. Check, make sure you've got that degree. And now, reminder of what we just found. We found the degree theta that the two vectors make, okay? The angle that's between those two vectors is provided in the problem. Okay, and it'll be between 0 and 180. It won't be greater than 180 when we do it. Are there any questions about that? Your turn, you're doing B in a like manner as you go. In a like manner. Just to practice. Get that view a little bit. That was a good smack. That sounded like I really whacked you, didn't it? Hurt my hand more than it hurt you. You're solid. Oh, at least I'm staying consistent. Now, as we get this going, let's go for theta is equal to the inverse cosine. I got my -5. I suppose I wanted to do that. And I got my square root of 5 and my square root of 10. And I go ahead and do my inverse cosine, and hopefully I come up with 135 degrees. The angle between the two, are we okay? Any questions about how to find the angle between two vectors? Now, let's talk about what happens the next step. If the vectors u and v are perpendicular, that is, if the angle between them is 90, then their cross product is going to be 0, okay? And when you do the cosine of 90, you get a 0, right? Because it doesn't go left, it doesn't go right. So either the cross product, or dot product, I should say, I shouldn't say cross product, the dot product is 0, or you've got 90 is your angle. So you got to just be careful as you're doing the evaluation. But if we get 0, we're going to make that assumption that we got a degree of 90 degrees. It's perpendicular. Now let's talk about the vectors u and v are called orthogonal. Okay, if you're going to make your teeth straight, you go to an orthodontist. Orthogonal, we're just making them straight. Okay, so it's 90 degrees. If and only if the dot product of UV is 0, so they're orthogonal, which means they're going to be perpendicular. But here's an interesting thing. The terms perpendicular and orthogonal almost mean the same thing. The 0 vector has no direction angle, okay, because it doesn't know where it's going. If you want to think about that, it's got 0 direction. Okay, so technically speaking, the 0 vector is not perpendicular to any vector. However, the 0 vector is orthogonal to every vector, okay? Except for this special case, orthogonal and perpendicular is the same. So we don't consider the 0 vector perpendicular to anything, but it's orthogonal to everything, okay? And it's because the 0 vector has 0 direction. As soon as we do a dot product with it, then we can prove orthogonality because the dot product is 0, okay? And that's what they're getting at. Okay, two vectors are parallel if one is a scalar multiple of the other. Okay, proving vectors are orthogonal. we can do this, but let's talk about this one for a second. If I'm talking about two vectors that are parallel and they're just scalar multiples, say I have vector 2, 3, okay, and I'm comparing it with another vector. It's just a multiple of another one. So if you pick a number like 4, if I have this as 8, 12, and we're talking vectors, excuse me, I can just compare to see if there is a multiplier that goes between the two. And that's, they have the same slope. If I go b over a, the slope would be the same. 3 over 2 would equal 12 over 8. And I can just show that it's a multiplier difference, whether it be positive or negative. Okay? The difference is just that, you know, they're equivalent fractions. Okay? It could be reduced to the other. But for this one, this next problem, what I'd like you to do is prove that the vectors u and v are orthogonal by finding their cross product. Or dot product, excuse me, not cross product. So, dot product. Yes, sir. Oh, we really got that with that. I must have gotten rid of that. Yeah, in this particular case, it would be 10. It should be 10. I must have just bleeped that right off. So you had 2, what did you have there, Klaus? 2, 5. And then you had 4, so the next one has to be 10 as you fill that in. So I apologize for, when I cleaned up the notes, I must have just bombed it right off. So you go ahead and do the dot product of those two. And you're finding whether they're going to be 0. If it's 0, they're orthogonal. If it's not, they aren't. And that's the check. This next piece, we're doing an exploration. In 618, angle ABC is inscribed in the upper half of the circle. Do you have any recall of the angle value of an angle whose vertex is on the circle with the interception of the arc? You guys recall this at all? The arc intercepted is twice as big as the angle whose vertex is on the circle. So if this is at the diameter, it's intercepting an arc of 180 degrees. So what's half of 180 degrees? It's 90. So I'm saying right now, this is already 90. And we're going to step through and we're going to talk about working with dot products and to see what the results are. Okay, it's a 90-degree vector right now. And that's any, you know, at least these two vectors, I should say, meet at 90-degree angle. Okay, if I were to make A2, I got -2, 0, and 2, 0, if A was 2 for my radius. I'm asking here, find the component form of the vectors u and v, and the component form for the two, remember head minus tail? And I'm asked to go from B to A. B to A, the head, -8, minus tail, -x. The head, 0, minus y, okay, but it would be -y. So that's my component form for BA. And I have component form for my BC as well as I step through this. So I'm going to use component forms to get these done. So I got my component form of the vector. Notice that I dropped the 0. 0 times minus y is just minus y in both cases. And I'm using the head minus tail rule, okay, that we worked on last Friday. Now, finding the dot product of u times v. You can conclude, what can you conclude about the angle theta between the two vectors? So if I do a dot product, I'm just going to take this times this. So I'm doing FOIL, -2 times -x. and negative y times negative y. I'm adding them together. Okay, so that's my step. At negative 2 minus x times 2 minus x. So I'm going to have negative 4 minus 2x plus 2x, that's 0. And so I got negative 4 plus x squared plus y squared. So I step through that. These two will become 0. So I got negative 4 plus x squared plus y squared. Okay. Now, as I look at this, I got to keep in mind something, what I'm doing. They told me here that A was what? As I'm going through. Because you got to keep in mind that when I'm going through this, I know x squared plus y squared is equal to my r, which was 2, right? So r was 2, and that is my equation of my circle. So since my radius is 2, where I see x squared plus y squared, and that's 2 squared, excuse me, I can substitute 4. So I got negative 4 plus 4 is equal to 0. And so they're asking me about the dot product of these two vectors. Okay? Well, before we even started, we knew they're 90 degrees because of properties from geometry. Now we've confirmed that when I have two vectors who are 90 degrees, their dot product is actually 0. And where in the world did I find it? Remember, at the beginning of this, I was talking about A being 2, and that's the radius of my circle. And the general form of a circle centered at 0, 0 is x squared plus y squared equal r squared. So I used the substitution there to make it work. Okay? Now, I know at this point that u, v are orthogonal, or the angle between u and v is 90 degrees. But we knew that before we started. And then this last one, repeat parts 1 and 2 for an arbitrary a. So which means that instead of putting in 2, use just a for it. So you're going to be prepping it this way as you step up. And then just go ahead and do the math with the FOIL with manipulation to find out what's happening. And remember, at this point, x squared plus y squared would equal to a squared. So you'd be using the idea of x squared plus y squared is equal to your a squared, because a is your general radius for any value, a. Okay? So when you get to the end, you'll be able to make that substitution. So check that out and see what happens. Now, keep in mind, we used it for a specific value to learn what's going to happen. But when we use a general value like this, we're actually proving that when we have the vertex of an angle on a circle and the rays of that angle encompass the diameter of the circle, the angle made is 90 degrees, and we're proving it by using vectors. And we're proving it for any size circle we ever come across by doing it this way. So again, my multiplication comes out, ax minus ax, that's 0. So I've got negative ax squared plus x squared plus y squared. And we just talked about the fact that my x squared, y squared is a squared, so I get to substitute that in. And I find that my value is 0, as we would surmise, because it works in every situation. I think I've already made my point. Okay, done with notes for what we have for today and for the year for you all. So all new material is complete. Okay, I know for some it's sad, for others it's very happy. It's an interesting look. But I hope continued success on what's going on. Now remember, tomorrow, Wednesday's a review day, and the review assignment's up and the stuff is posted. And then Thursday is a short quiz on 6162. You should be done within a half hour. Okay, it's pretty basic on the stuff that's in there, so pay attention to the stuff that's in the review, because it's pretty much telling you these are the things on the quiz. Be ready for your final part A, which is 1, 2, 3, and 8, and those answers are posted for Thursday's class. Those answers are already posted. Okay, for what's going on with them. If you have questions, work through them, ask me, we'll see what we've got, but those are the ones I'm going to focus on this week, 1, 2, 3, and 8. On Thursday, for those people leaving early, I will have 4, 5, and 7 available for you. Okay, because people will be going away for the weekend early and having that long car trip wherever they're going. So I'll have those available for those people who are going to be gone. I'll also have available people in class on Friday, because I want to make sure you have time to schedule for yourself so you can just work through stuff and be ready for your second part of your final next Friday. Or if you're leaving or needing to take it early, I'll be available to do that too. You'll just take a different version of it, last year's version. Okay, any questions? All right, great. Thanks. Have a great day.